Welcome to the Foundry by Forge College. Let's jump right into today's explainer, which is a really crucial one. Patterns for synchronized data handling. If you've been tracking with us, you know this is a key piece of our module on interconnectivity with Solana components, sitting right at the heart of the Exploring Turbine track. Today, we're taking all that high-level architectural theory we've been talking about and turning it into concrete, measurable engineering tactics. Basically, we're building the exact toolkit you need to keep your decentralized systems perfectly in step.
Okay, let's dive into this by anchoring ourselves to exactly where we left off. In our previous explainer on designing cohesive network architecture, we hammered out a really specific concept, the synchronization surface. Remember, this is a named point where a component accepts, validates, or publishes state changes. We took all that murky implicit data sharing that usually plagues distributed designs and forced it into explicit, observable interfaces. But identifying a surface is really only half the battle. Now we have to decide exactly how the data actually flows across it without causing total chaos.
And that brings us to the central question of today's explainer. How do you keep a decentralized orchestra playing in perfect harmony? Because, let's be honest, if even one single musician is out of tune, or worse, playing an entirely different song because they missed a cue, well, you're not making music anymore. You're just making very, very expensive noise on the blockchain. When we build these complex distributed systems, every component absolutely needs to know exactly what the others are doing, and more importantly, what they're going to do next.
So, here's our agenda for today. 1. The Solana Data Orchestra. 2. Strict scores and local improv. 3. Rehearsals, streams, and retries. 4. Metrics for musical harmony. 5. Building the evaluation table. And 6. Conclusion and next steps. Let's get to it.
Section 1. The Solana Data Orchestra, mapping the metaphor to the machine.
To really wrap our heads around these data synchronization patterns, we need a strong mental model. And honestly, the orchestra metaphor is absolutely perfect for the machine we're dealing with. Just think of every Solana component or microservice as an instrument section in our orchestra. Those synchronization surfaces we defined earlier, those are the conductor's cues and the published sheet music. And the network protocols, like Turbin's block propagation, they act as the acoustic paths that actually allow the brass section to hear the string section across the network. The sheet music is our authoritative state, and the conductor's hand signals are the fine-grained timing decisions that keep everyone perfectly aligned.
Section 2. Strict scores and local improv, the primary synchronization patterns.
Keeping that model in mind, let's look at the actual engineering patterns we use to achieve this decentralized harmony. We have operational choices to make at every single synchronization surface. There's a specific catalog of 5 primary synchronization patterns that you can apply. We've got canonical-source updates, optimistic delta propagation, version snapshots, change data capture, and idempotent message propagation. Each of these tackles a very specific challenge and carries its own unique trade-offs. Let's break down the first 2. Now, what's really interesting about this first one, the canonical-source pattern, is just how rigid it is. Think of this as a single master-printed musical score, kept under lock and key in a highly secure library. If a section wants to play, they must fetch the latest edition from this exact source. In engineering terms, this enforces strict, single-writer boundaries for domains where you absolutely cannot afford conflicts, like the ledgerhead. It's incredibly predictable, for sure, but the trade-off? Everyone has to wait in line at the library to get the updates.
Contrast that strict master score with optimistic delta propagation. This one is like a musician just improvising locally and instantly broadcasting a short recording of their solo. It's a real game changer for high-throughput, user-facing flows where low latency is everything. The system basically just assumes the write will succeed and pushes the delta forward. However, this flexibility introduces split brain risk. If that improvisation clashes with the rest of the arrangement, the system has to quickly detect it and issue a rapid reconciliation, kind of like a retake, to fix the harmony.
So those 2 patterns were great when everyone is actively participating, but what if the network is just being completely unreliable? What if the entire trumpet section oversleeps, completely misses the conductor's cues, and just stumbles in halfway through the symphony? You can't just hand them a delta update. They don't even know what song we're playing.
Section 3. Rehearsals, streams, and retries, handling complexity and recovery.
First up for recovery is the version snapshot. Imagine the conductor actually pausing everything to hand out a complete, full-length rehearsal recording to anyone who just walked in the door. In system terms, these are periodic full-state checkpoints. It's absolutely brilliant for cold starts or bringing a disconnected node back up to speed fast. The catch? Distributing a massive recording takes a ton of bandwidth. You're basically trading heavy network consumption for incredibly fast resynchronization.
Next, we have change data capture, or CDC. If a snapshot is a giant recording every hour, CDC is a continuous flowing stream of sheet music mutations. It preserves the exact order of every single state change without requiring downstream consumers to run massive full database scans. It is the perfect pattern when you need strict auditability or when you're feeding incremental data to processors that rely on precise sequential history.
And rounding out our catalog is idempotent message propagation. Let's say your acoustic path, your network, is super flaky. You might need to shout the exact same cue 5 times just to make sure the percussion section actually hears it. Idempotency means you can safely blast those retries because the receiving system is smart enough to just suppress the duplicates effortlessly. It beautifully converts messy, at least once network delivery into safe, predictable, effectively once processing.
Section 4. Metrics for musical harmony. Measuring the trade-offs.
Now, architecture isn't just about picking patterns. It's about proving they actually work under pressure. Every single pattern we just talked about forces you to pick your sacrifices carefully across 3 core trade-offs. First, consistency versus availability. Do you wait for the master score and increase latency, or play immediately and risk being wrong? Second, bandwidth versus reconciliation cost. Do you send giant snapshots or tiny deltas and pay the CPU cost to fix conflicts later? And third, determinism versus flexibility. You literally cannot have it all. You have to measure exactly what you're trading away.
To measure those exact trade-offs, we map our orchestra metaphor directly to observable system metrics. The delay between the conductor waving their baton and the back row playing a note, that maps right to propagation latency. The length of a musician's unverified solo, that's your delta message size. And the time a section spends reading outdated music is your staleness window. Actually exploring how to instrument these exact workflows is a core focus of the deeper learning programs we run over at Forge College, where we turn all this theory into hard data.
Section 5. Building the evaluation table, the performance artifact.
And this brilliantly illustrates what that artifact actually looks like, the prioritized evaluation table. You list your pattern on the left, map it to the architectural rationale, like exactly why you chose a canonical source. Then you clearly define the metrics to observe, such as propagation latency. Finally, you assign a priority based on your risk posture. This table isn't just some checklist, it's an instrumented contract. It forces you to write down exactly what you expect to happen before you run a single performance test.
To build that table, we condense the engineering workflow into 4 punchy milestones. Step 1. Inventory all your synchronization surfaces. Step 2. Map 2 to 3 feasible candidate patterns to each surface. Step 3. Define the specific metrics that prove the pattern is working. And Step 4. Set the thresholds. Decide in advance that your latency guardrail is, say, 50 milliseconds, so you know exactly when your system is failing the test.
Section 6. Conclusion and next steps. Preparing for turbine performance evaluation.
So, we've covered a ton of ground today, moving from abstract orchestra metaphors all the way down to a highly practical testing artifact. The crucial point here comes down to 3 guiding principles. First, match the pattern to the strict invariance of that specific surface. Second, measure exactly what your mental model predicts. If you chose optimistic deltas for speed, you have to measure your reconciliation frequency to make sure the speed is actually worth the cleanup cost. And third, treat your evaluation table as an instrumented contract that validates your assumptions with raw data.
This all sets the stage perfectly for our next explainer, Performance Evaluation Foundations for Turbine. Your homework is to draft at least 1 or 2 rows of this priority table. Inventory a surface, pick a pattern, define your metrics, and bring that annotated clipboard with you next time, because that is exactly the input we'll use to design our live experiments.
I'll leave you with this final provocative thought. Are your components playing in perfect harmony, seamlessly sharing a single canonical score, or are they just making expensive, unsynchronized noise on the network? Thank you so much for joining me on this explainer created by Forge College. I highly encourage you to head over to forge.college to learn more about this subject, dive into our courses, and explore a whole range of other Web3 topics. Until next time, keep your systems in sync and your metrics sharp.